Hey, thank you for coming. I want to talk about the Linux kernel today, Rust in the Linux kernel, and Arc. So, yeah, it's something I've been working a lot on recently. A bit of context. So, the Linux kernel, it's a kind of a special place. For a long time, they had this rule that you had to use the C programming language to develop code there. But it's no longer the case, right? Now you can use Rust. I have some info up here. Yeah, it started in 2020. Then they said that I have C in 2021. In 2022, they actually said, yeah, let's try it as an experiment. So Rust is in the kernel as an experiment right now. And so in my case, I'm working on one of the Rust drivers. It's called the binder driver. It's used for Android for sending messages between processes. But that's not really what my talk is about. Because, Rust in the Linux kernel, what does it take? So real Rust drivers used in the Linux kernel, that's really, really important. Right? If nobody uses it, they're just going to rip it out. But that was my previous talks. So that's not what we're talking about today. Today, I want to talk about, the Rust language and what happens when you put the Rust language into, let's say, a new environment, which the Linux kernel certainly is. There are various things, good first impressions, Back when we started, you had to use unsafe blocks every time you created a struct because, working with the C types and so on. So we don't do that anymore. That's a pretty bad impression if you have to use unsafe all over your code. Now, what I'm really talking about today is Arc. But specifically, unstable compiler features related to, I'm going to deep dive into Arc, but, it's a general thing. And it's actually, it's a problem for us that we are actually requiring a specific version of the Rust compiler because we have to support, the unstable features, right? And they change when you upgrade the compiler, unlike stable Rust. Now, it's not actually as bad today as it has always been. We used to have our own, forked version of the alloc crate of the standard library, and the standard library uses a lot of unstable stuff internally. We're getting rid of that fork, so hopefully the amount of churn related to specific versions will go down a bit. But that we still need a bunch of unstable features, so it's a problem. And to understand why is this actually a problem, we're Rust developers. We know how to, we just do Rust up and that's it, right? But, once you're a distro that wants to ship Linux and they want to use Rust in their Linux build, right? They're not going to use Rust up in their distro builds. They're going to use their own Rust compiler. What are the chances that the Rust compiler they ship match what the Linux kernel needs? Well, if we supported a fair number of versions, the chances would be pretty good. But today, the chances are very low. And even if they match today, in a few months, they're not going to match. And this problem goes on and on. There are also cases like when somebody who does C code submits a patch to the kernel, we would like them to, compile their code locally with Rust enabled before they send that patch. Maybe they change the header file that broke some Rust code. But they're not gonna bother if they have to go look. If they can't just use the one from their distro, a lot of them are not going to bother. This is just some of the problems. Anyways, enough about that. What am I talking about today? Essentially, I'm going to talk about why is the Linux kernel special, right? Why is it that we don't just do the same thing as you do in normal Rust? Like, why don't we just use the standard library arc? Well, today I want to talk about what makes the Linux kernel different. And then at the end, I'll mention some specific unstable features that hopefully are on the path to being stabilized. Now, I promised to talk about ARC. ARC stands for Atomic Reference Count. The idea is you have some shared value. And so you can have many ARC handles that reference the same shared value. So normally the shared value is immutable, but you can make it mutable. And one of the benefits of having it shared is that not only do you use memory many times every time you clone it, but also if you modify it, all of the clones will see it. So the way ARC works is that when you have an ARC, you can call clone, and then you get another ARC. But it doesn't actually do a deep clone. It doesn't clone all of the data. That's the idea. And so then they get destroyed, the counter goes down. When the counter goes 0, the destructor runs and cleans up the memory. That's all an ARC is. Now, the standard library for Rust has a type called arc that works like the one I just showed you, but it's special. You can't implement your own. Or at least you can't implement your own fully featured version. So yeah. One reason is, so this counter, what happens when it goes all the way up to the maximum number? Well, it wraps around to 0, and now you have a lot of handles, but the object got destroyed because you had a 0 in the counter. So what Rust does is that when this happens, it just calls abort, so it kills the program. So in the Linux kernel, they also have reference counting. It's not a Rust-specific solution, but in the Linux kernel, they have a different way to handle it, and we would like to use the Linux kernel's solution, the solution that the Linux kernel has agreed to use for reference counting. That's what Rust should be using too. And for example, when it hits the maximum number, we replace it with some special infinite value, and then it just stays there forever. And this way, it never wraps around down to 0. Now, so when this happens, the value can never go back to 0, so the memory never gets cleaned up. But that's better than calling abort, right? What happens if you call abort in the kernel? Well, your machine just turned off. So this is also a bit of a technical issue. So there's this whole issue with the memory model. The Linux kernel came up with their own memory model for how to use atomics. And we're supposed, we discussed for a long time, should we do what Rust usually does for atomics? Or should we mirror what C does? And what C does involves some inline assembly, and it's kind of, let's say, specific to your architecture, but it works for them. And we came to the conclusion that we really should use the same atomics as the rest of the kernel. There are many good reasons for this, but the point is, the arc is not doing that. And so that's another reason. They're also nice to haves. When you work with C types, a lot of these C types build in some sort of assumption that their address doesn't change because, well, they're stored in some linked lists or whatever. But the point is, they require this thing called pinning, which a lot of you have probably heard of, and a lot of you probably don't know the details of. But the point is, we need pinning all of the time. And so we made our arc include pinning by default. Now, you could do this with the standard library, but just, wrapping every arc and pin. But it's nice to have that we can do it in our own way. Another nice to have is weak pointers. So a weak pointer is when you have a reference that doesn't prevent the value from getting cleaned up. We don't really need this, and in implementing it involves several counters. Removing it simplifies our arc, so we don't have it. Now these unstable features that you actually need to implement your own fully featured arc, we also have some other types that we want to use them for. So stabilizing these features would also let us use them for them. Let me tell you about the first unstable feature. It's called arbitrary self-types. So if you've used Rust at all, you've probably seen &self and &mute_self. But you can also write functions like this: self, arc, and self. And this basically means that instead of an immutable reference or a mutable reference, you get an atomic reference counted reference when you call the method. This is very nice because, when you have the arc, you can call self.clone inside the function. So this is a nice thing. Now, this particular example I showed you, we could work around this. It's not a be-end and end-all thing, right? But it's still nice to have. But as you will see later, there are some other cases where we actually do need the feature, and it's not just a nice to have. Now, to an entirely different topic, linked lists. So linked lists are hard to implement in Rust. They're famous for that. There's a whole book called Learn Rust with Way Too Many Linked Lists. Sometimes when people want to learn Rust, they say, oh, linked lists are simple, right? I'll start with implementing a linked list and then they'll have a bad time. But anyways, and you don't even want linked lists most of the time because they have worse performance than vectors. But the kernel still needs them. And the problem is we have something very special that you don't have to deal with in user space called atomic context, which it's basically a short amount of time where your thread is taking up the entire CPU core. Like nobody else can run here, so you can't context switch, that is, replace the thread with another thread during this critical region. Okay? And one of the consequences of this is that you cannot allocate memory, at least not with the standard ways, because allocating memory might call into stuff that will do a context switch. Now, imagine that you have a vector here. Now, so one example of this atomic context is what's called a spin lock. And a spin lock is kind of like a mutex, if you're familiar with that, except it's, super fast. But while you have the spin lock, you're in an atomic context. And so let's say inside the spin lock, you have a list. And I want to push a value to the list. Well, how do you actually implement insert on your list if you're not allowed to allocate memory? So if you're using a vector, the problem is the vector has some amount of free space, and there might not be enough. And if you run out of space, you have to allocate memory, but you can't. So what you have to do is return an error, and then you can leave the spin lock, make a vector with enough space. Then you can re-enter the spin lock, copy all of the data over, and put it in. You could do that. But well, this gets kind of cumbersome, right? Because now if you did anything inside the critical region before you try to call push, then if you get an error, you have to undo it. It's it's not so nice. But with a linked list, that's no problem. Right? Because with a linked list, here's a linked list. You have these next pointers and previous pointers that point to the different items. I have a new item down here I want to insert. So I just, change the pointers. No allocations is needed for that. Like this object is already in an arc somewhere. So it's already allocated a long time ago. So that's easy. Yeah, so it looks like this is the idea. We have linked lists in the kernel. And so this is a super simplified example of what it actually does, but the idea is you have 2 pointers. They're actually wrapped in like a struct, but they have 2 pointers. And then we put this thing in an arc. And then to insert, we just update the pointers, and that's it. Very nice. But there's a problem. The problem is you can have many arcs to the same value. I mean, that's the entire idea. That's why you're using an arc, so you can have many references. But what if you have 2 clones to the same shared value? Well, you only have 1 pair of next previous pointers inside the value. So what happens if you insert the 2 clones into 2 different lists at the same time in parallel? I'm not going to go into the details, but the point is you're going to have a bad time. You're going to have a data race, then which list does it end up in? Maybe both? I don't know. Your lists are corrupted now. Don't do that. So the solution we came up with is a new smart pointer, like the arc, called the ListArc. So you can have many arcs, as usual, but at most one of them can be a ListArc. And so the idea is that the previous next pointers, they're kind of owned by the ListArc. Right? And Rust's ownership model works very well for this because the ListArc is like an object. You can transfer ownership. And so you always have a single object that has ownership over the previous and next pointers. And so if you want to insert this into a linked list, you just pass the ListArc to the linked list. And then nobody else is using the pointers right now, so we can insert it. Why do we have these linked lists? At least why I use them is this queue of events. So we get we have a bunch of events. We put them in a queue. The linked list ensures we have an ordering, and we're using a linked list because the vector runs into this problem with atomic context and allocations. Okay? Now, when you have a queue of events, you probably have many event types. So it's really a linked list dyn event trait. And so this gets into the other unstable feature. Because now we want to use dyn trait with arc. Right, so it looks like this, right? We saw this before. So we have a trait called event trait. And it has, a run function or whatever. And then we have self::ListArc. We saw this before. That's this unstable feature called arbitrary self-types that lets you put the, arc, or in this case the ListArc, as the argument. Now, of course, the ListArc, it's important to, move around ownership, right? Like, you only have one. So if you don't pass it into this function, well, the function now doesn't have the ability to, use what the things that ListArcs give you permission to. So because of that, we can't just use &self. Yeah. So the point is, when you have, so the way it works is you have a ListArc of your event struct. It's some struct containing the event. And then you want to convert that into a ListArc dyn event trait. But that conversion, it works with the standard library arc, but adding that conversion to your own types is unstable. So here's one unstable trait. So all of this at least the way it works right now in the compiler, is that we have an unstable trait, coerce unsized, so that for coerce is this conversion operation, and turning a struct into a dim trait is an unsize, so that's why it works. It's called like this. And we want to, implement this trait, and it's all nice. We also need another trait. This is so when you call the trait function, right, you already have a ListArc to an event trait, right? But when you then call it, then inside the function, it's actually going to be it's going to look up what's the underlying event type, and then it's going to go into the code where you know what the event is. So now you actually just did a conversion from ListArc dim trait to ListArc event type. And that's what this trait does. So dispatch refers to, looking up the function with the right event type. And you may not have noticed, but there's another trait here called unsize, and that's also unstable. Okay, well, so we came up with a solution. We discussed this a lot between the RustNL people and the language team. And the solution that was proposed is the thing called Derive smart pointer. Because the problem is, we have these 3 different traits. And we don't even know, we know that the way they look right now, that's not what they should look like when they're stabilized. Right? But that makes it kind of difficult to stabilize them. Because then you have to sit down and think really hard about designing programming language and figuring out what do you do about that. What's a better design? And then you have to implement that. So, that's been tried before. There's a pre-RFC up there about attempting to do that. But our proposal is, we need this today. Can we stabilize, can we take this large feature with these many traits that we don't even know how to look? Can we reduce the scope? Right? When you don't know how to do the thing you want to do, reduce the scope. And so what we're going to say is, we add this macro, you put it on your struct, your ListArc struct and your arc struct, and that's it. This macro generates these traits behind the hood. But the macro is shipped with the compiler, so it can be special. But we don't stabilize what the macro expands to. And this is, kind of unusual, but it's not totally unheard of, because, we have a test macro for tests, and that actually expands to some unstable stuff related to the, benchmarking suite and testing suite. So they can change it in the future. And so this idea is simply, make it so that we can start using the feature now, and we can continue working on the underlying traits. Don't lock us in on one specific answer. So, just before RustNL, I posted this RFC, proposing to add this Derive macro. So I'm hoping that will be stabilized soon. And that's it. Go take a look. Yeah, this is the end. In case it wasn't clear.
Well, let's see. Okay. Any questions? Here's a question. Yep.
1, 2. Thank you for your talk. My name is Vlad, and I'm with Rust for more than 10 years. I think I started to learn Rust even before 1.0 stable release. And at that time, I already was surprised that in Rust there are a lot of magic around standard smart pointers, for example, box. And for example, you can move a value out of the box. And there was a lot of RFCs to fix them. For example, implement the ref move for box pointer. but they were left without any moves, or even were rejected because there wasn't any practical value. So what do you think? Is it good time to get rid of all the magic around all of the pointers, including box? Is it beneficial for the language in general? What do you think? Thank you.
I mean, I do mention in my IFC that, reducing the magic of the standard library is nice. And so, yeah, box is an example of something that's even more magical than arc, right? Arc is a bit magical, but box is really magical, right? You can move the value out, which is like the only thing place where you can do that. Yeah, it's kind of like, we don't really need it, right? We're working hard on stabilizing the things that we actually have a real reason, like, that we need a lot, right? And this is something we need a lot. Yeah. I think it would be cool to see movement on, and maybe this, making progress on this smart pointer issue can help others to, move on other smart pointer issues. I do also, this issue doesn't really cover smart pointers containing custom allocators. That's also a future possibility.
Then we have an online question. Someone is asking that at the start of the talk, you said that the implementation of Arc aborts whenever the reference counter reaches I size max. Why is it an I size and not a U size?
Okay, hold on. Okay, so the basic idea is, like, I size max is basically, halfway around the integers, right? So you have up to I size max, and then you have just as many numbers above that. And so the reason for using I size max as the, let's say, threshold where you do, like, special stuff is that, for one, like, if you hit this number, it's still a bug, right? On the other hand, if you use U size max, right, then let's say that 3 threads run in parallel, hit increment at the same time, well, some of them are going to see, oh, the ref count is 1, right? Because it wraps around, and the other thread is going to call abort soon, but hasn't done so yet. And so using I size max means that now you have to call increment in parallel from, what? Billions of threads in parallel for any of them to see it actually wrap around, right? So it kind of gives you some time to call abort before the other threads see it actually wrap around.
Any more questions?
On one of the slides, I saw a struct with an intriguing name called unique arc. And since arc is all about putting more than one thing in there, I was wondering what that's about.
Good question. I can't find it. Well, whatever. So the idea is, let's say you make an arc, right? Or like, here we go. So let's say you want to create an arc inside an atomic context, right? You can't allocate memory there, but creating an arc requires that. So what you do is that first you create a unique arc containing, uninitialized memory, and then in here you initialize the memory and then you convert it to a normal arc. Does it make sense? Right, because that way you allocate the memory beforehand. Yeah, and so it's kind of like this idea that it's unique for some time. It's also how you create the list arcs, right? You take a unique arc, then you convert that to a list arc, because now you know that there's no other list arc out there, right? Because the unique arc is unique.
There's a hand there.
So from this talk, it appears that there's a lot of effort involved in getting Rust into the kernel. So thanks for that. I was wondering about the process of getting this accepted and also getting some foundations for. I mean, there's a lot of contributors. So do you still experience that there are tribes of like the old C camp, and then now there's the Rust camp, or do you think it's right now a joint effort across the kernel to get it in there?
I mean, that's a reason I try to say the Linux kernel needs rather than the Rust for Linux needs, right? But, there are the people who come, into the Linux kernel from Rust. And there are people who, have worked with C for their entire lives and now need to learn Rust. Right? It's a different experience. And yeah, it's a real difference. That you're not just, it's not just gonna go away magically. And it's also why, right? Good first impressions for people coming from C.
Yep.
Right?
Yep.
It's there for a reason.
Yep. Thanks.
There's a hand there in the back. This is the last question.
Yeah, thanks for your talk. I think you use a lot of unstable features probably. What is actually your most favorite unstable feature which you hope will get stabilized? Thanks.
The thing I want to see most stabilized?
Or what you find, either what you want to get stabilized the most, or what you find most joyful to use. Whatever you want.
Well, I put a lot of effort into working on this IFC and pushing this particular feature forward. So that's certainly the one I have, let's say, invested the most in. We also have some features where sometimes people say, maybe we should use this feature to do this cool thing. And then I say, let's not do that. Let's not use min specialization, right? Let's not make that one of our blockers, if we can help it at all, right? Because some features are harder to stabilize than others.
Excellent. So I guess this is the moment to thank you again for the talk. And please end this.